Welcome to another Tech Command Investing. I'm Alain Gavin, managing partner at Scion and venture partner at Carista. And this is a show where we explore how emerging technologies are reshaping security, business strategy, and European resilience. And today, very proud and also happy to bring back somebody we invested in a long while back. And again, he has shown his mettle and made his point very well and got a good founding round with Seraphim and Scout Ventures. We're talking about AI that almost nobody is talking about. And that might be exactly the point. While the world is rushing or stampeding towards hundreds of billions into generative AI, giant models, giant data centers, and you saw the Colossus from Elon, and then coupled with that giant energy bills, my guest has taken the opposite bet. Johannes Waldstein is the co-founder and CEO of PiLogic, a Los Angeles-based company building what they call exact AI. That means mathematically precise, expert-guided artificial intelligence that runs in milliseconds on a sliver of the compute and never hallucinating. Because when your product is keeping $100 million satellite alive, probably right, just won't cut it. So PiLogic raised $4 million seed round last year in May, with Scout Ventures and Seraphim leading the round, and Sovereign's Capital, Flex Capital, FN Capital, and Super Angel Gokul Rajaram joining the round. And just last month in June 2026, the US Air Force Research Laboratory signed a 2-year agreement with PiLogic to test whether its exact AI can diagnose and predict electrical failures on spacecraft, the kind of failures that today quietly kill satellites because a handwritten rule never fired. Behind the technology is a remarkable pedigree of co-founder also Mark Chavira, who's the CTO and spent years at Google and Raytheon. He did his doctorate at UCLA in probabilistic AI and co-authored the NASA research paper on which this whole field is built. Johannes himself is a serial founder, as I mentioned before, 5 companies, 2 exits. And Mark came out of semi-retirement because he believed this was the one. The probabilistic inference had been cracked. The 2 main problems: model building and scaling at the edge. In our current geopolitical fields, the timing could hardly be sharper. GPS jamming across the Middle East has exploded since February. Ukraine remains the densest electronic warfare environment in history, and Russia is one of the leaders in that field. Washington is architecting the Golden Dome, and NVIDIA-backed StarCloud has just put the first data center class GPU into orbit. Every one of those stories runs through the same question: can machines reason exactly at the edge when it matters most? This is Tech Command Investing, and this is PiLogic. So, Johannes, great to meet you again and see you on my podcast today. I'd like to just first dive into your vision as a founder and the idea around Bayes. Yeah, you founded 5 companies over 2 decades and had your exits. You had an exit and we're looking at what to do next. Mark was a semi-retired from 13 years as director at Google. And then you met both. And as I understand, Mark and your sons were in the Scouts. So not
Yes.
Mark.
Yeah, Mark's sons were in Scouts. Yeah, we've known each other for 10 years, and I was always trying to get him to leave Google and start a company, and he was always saying Google's the best place in the world to work, which
Yeah.
was true until COVID, and then it became a less fun place to work. And interestingly, he and I were both looking at automated reasoning. I was researching Byron Cook at AWS, one of the few companies that are really pushing automated reasoning forward, more on the logical reasoning.
Mm-hmm.
And what AWS found was, instead of testing things millions of times and trying to find the edge cases, you could have a logical proof and prove that no one had access to your system, or that only the right people had access to your system. And so I was interested in logic and determinism and deep niches. What's amazing about machine learning is it feels a little bit like magic. You can ask it anything. It has broad applicability, but it doesn't have great depth. And so I was looking at logical reasoning and automated reasoning. And Mark said, I have a PhD in this and I have the best inference engine in the world. I've been tinkering with this. And so both of our interests came together. His was much longer in that field. And for him, it was really, how do you bring real impact to some of the areas where machine learning doesn't work well, where you don't have a lot of historical data or you have no data on the edge cases.
Mm.
Rules are pretty brittle, so you have to think of the if then ahead of time. You have to think of, does it work like this or does it work like that? And it's not good under uncertainty. So something that works well under uncertainty, that works well without a lot of historical data, and that is exact in that it's actually doing the math of the probabilities rather than approximating it or looking at something that's associative. It's not just saying these things happen together, but I believe this thing to be the cause of this other thing. So not just association, but looking at causal
Mm.
relationship. So Mark and I came together around that. We now have a handful of government customers. Air Force Research Lab is the one that's been made public. There are a few more that will be made public in the next week or two. And we have several big commercial customers as well that will be announced. And
Mm.
the need is really great. As you were saying, Alain, we are being pushed towards secret and top secret for some of the military use cases. But even in the commercial space, if you put up a data center, if you put up something like that, you need it to not fall apart. You need it to self-heal. You need
Mm.
it to understand what's going on beyond what a human operator on the ground can do. And then our models are so light that we can push a model. We've pushed models up to customers up in space. And Space Command is interested in this because they have thousands of satellites with no GPU, and they want to run advanced analytics. They want to run sensor fusion and tracking. They want all of these capabilities.
Mm.
And a machine learned model is too big to push up and run on those thousands of satellites, where a very light mathematical model, like the Bayesian inference models that we do, we're able to push them up to an existing satellite. So not only is it the new entrants like the Star Clouds, the Sophia Spaces, who are building data centers, but it's also the billion-dollar government satellites from the Boeings, Lockheeds, Raytheons that are up there that want more capability, and now PiLogic are able to have more capability.
Yeah, following on from that, before we go anywhere near satellites, let's do something we've never done on this show. The whole company is built on Bayesian reasoning, a piece of 18th century maths. I looked it up, yeah. Most people have never heard of. Johannes, can you explain, like I'm a 12-year-old, no equations allowed, how that works?
Yeah, so the big insight of Thomas Bayes, the inventor of Bayes' theory, is that you can flip probabilities. So humans are good at saying, if I do this, these consequences will happen or these effects will happen. And what Bayes' theorem does is it allows you to flip that and look at evidence. You
Mm.
understand a little bit about the prior probabilities of things. And so given prior probabilities and current evidence, to calculate the probability of something happening. And he did that in a very short, elegant mathematical equation. That
Mm.
was much further developed by Yuta Pearl at UCLA in the 80s, and extended that to do much bigger problem sets. And Mark, my co-founder, had his master's first at Stanford in this type of AI, and then went to Yuta Pearl and Adnan Darwich, the disciple of Yuta, really to study how do you scale this. So if we look at figure one, as you can see, if you're just listening to it, the figures are also downloadable in the description. So there are a couple different ways to make it as an easy example. One of them is Sherlock Holmes. If Sherlock Holmes just had rules, then he would have to get out his rule book and say, is there blood? Is there a knife? Is there... And if it
Mm.
wasn't one of those rules or thresholds, is the temperature more than this, therefore there's a fire? If Sherlock Holmes didn't have one of those rules, he wouldn't be able to solve the case. But what Sherlock Holmes has is something different. He has a bunch of principles from which he can reason. So if you're looking here, you have three possible murderers: the gardener, the butler, the cook. And now you start introducing evidence. So are there muddy boots? Do people have an alibi? And the probability of who did it immediately changes. And this is the way to a much more complex state the way our inference engine works, which is the telemetry is coming in on a satellite. It's not agreeing. Sometimes it's very noisy. I'll show you what the actual data looks like. It's a cloud of data.
Mm.
So the machine is a little bit like Sherlock Holmes, reasoning to what is going on in the system, given the evidence. And I've told the machine, this is how electricity works. This is how diodes work. This is how a battery works. This is how a solar array works. And so rather than using pattern recognition, either of historical data or trying to find the function, basically by training a machine, some of the world models, training it with data, and it learns physics or it learns the laws of electricity, our models are told explicitly, this is the way it works when it's healthy, and that's deterministic. It must function that way. If something's happening, the opposite of it can't happen at the same time.
Mm.
And so it's able to reason in situations that are very hard for humans to reason, and where thresholds don't work because the cloud of data is such that the threshold is never triggered because you're above and below that threshold all the time. So that's
And of course, it happens in milliseconds as well. Yeah,
and it
that's the
happens in milliseconds.
yeah.
So that's the challenge for the human operator. Has two challenges. One is there are lots of false positives and lots of satellites, and so you get lots of red lights, and you have to go investigate, and there's nothing there. So that's stressful and takes a lot of operator time. And then the second problem is some of the root causes are not immediately identifiable. Like we've done work with a large satellite vendor on thermal runaways. One of our government customers has lost two satellites, and the human operators weren't able to see the thermal runaway, and they lost the satellite. And we've been able to show that we can identify that early enough and go to a safe mode or a backup mode in order to not lose a satellite under those thermal conditions. And the reason the threshold never hit is because the human operator says if the temperature goes above X or above X band, then trigger. But the sensor's reading above and below that temperature, and so the threshold doesn't know what to do. And same with the human operator. If you look at it just with the naked eye, it's very hard to tell where is the temperature starting to run away versus regular fluctuations. And so you need something that knows about other parts of the system in order to triangulate and use logic and reason, um, in order to correctly diagnose that.
Yeah, and that's also the point about the satellites also worth hundreds of millions of dollars, right? So it's not just a small CubeSat, but it's the loss is extensive if they do lose it.
And that's
Um,
and that's where most of the interest at the moment is from the data centers and the larger satellites. So we have customers who are in very high Earth orbit or going into cislunar. And not only are those satellites billions of dollars, but it takes a long time to get
for
into
the
that
data to get
position.
there, yeah.
Takes a long time to get there, and then it's not just the cost, but it's the loss of capability. So if that's gone, then either the government capability or the commercial capability is gone probably for 2 or 3 years, and that's
Yes.
not acceptable for those customers.
Mm. And then moving on maybe to the next question around the contrarian bet that you've taken with exact AI in a world where we're bombarded every day about generative AI. Here's what fascinates me is the entire industry is basically going one direction: big models, data, more GPUs, and you went the other way. No training data mountains, no GPU farms, models measured in kilobytes,
Yeah.
something I haven't heard for a long time,
Yep.
that answers in tenths of the millisecond. Your investors at Seraphim called the approach differentiated counterintuitive in a world obsessed with generative AI. So make the case, where exactly does generative AI break, and exactly how does AI or exact AI win? Yeah.
Yeah, if we look at figure 2, again, those who are just listening can download it in the description. This is really a comparison of generative AI and its strengths and exact AI. And generative AI is amazing looking at just about everything. It has all of the internet, a huge base of knowledge. You can ask it anything, but it's not deep and it's not specific. And exact
And it
AI,
hallucinates.
and it hallucinates, which is a huge downside. It's imaginative, which is a strong way of saying um, it's hallucinating, it's imagining things, but
Mm,
there's certain instances where you don't want that. And
yeah.
so the use cases that we're looking at, you want to compute the exact physics of the flight and not approximate it or guess it. You want to do the actual math to predict where is that thing. Or when you're doing the logic of a system, you want the exact components of that system and you want precise answers, not approximate answers or what an intelligent person would say. And also in our instances, you don't have historical data. So we don't have large bodies of data on anomalies in
Mm,
space. And so you need an approach that can reason without prior data precisely about what's going on very quickly and with low compute. And so exact AI, the difference between approximate methods and exact methods is the exact methods are computing the mathematical probabilities or computing the physics of the problem rather than an approximate method, which isn't doing the underlying math, but is fitting a curve or fitting something that's close to that. Not to knock generative AI. Generative AI is amazing as a general coding agent or as an amazing language tool. And I think that's what attracts Sam Altman and a lot of these people to generative AI is they think of it as a super intelligence or a general intelligence or something that's like magic. It can do almost anything. But I think there's a strong sort of counterweight to that. AWS, for instance, with our automated reasoning group with Byron Cook, where people are realizing that for a deep vertical, you can't have something that's generic and you can't have something that hallucinates. And a lot of companies are finding this is in advanced manufacturing, this is in nuclear, this is in quantum, this is in high stakes. If you have something that's physics based, that's provable, that's much better than something that's approximate. And so a lot of those industries are using what would be called statistics or classical AI, whether that's logical inference like AWS, or whether that's rules plus statistics, like a lot of those other industries are using. So I think the big companies are still going to go after the largest TAM, and one of the reasons why we have so many moats is even though Mark at UCLA at that lab invented some of the ways to scale this and automate this, most of the students are taking that Bayes theory and constraining an LLM or mixing it with transformer technology and
Really? Okay.
agentic AI. And so a lot of the scientists are all focused on that huge, massive, shiny TAM. And aerospace and defense is a massive market, but it's relatively small compared to every human that codes or every human that would
yeah.
want to code but doesn't know how to code. That is almost the largest TAM you can have. And so those big companies are not focused on aerospace and defense is hard. They're long sales cycles. You have to know the physics of it. It takes years to know that. So we're focused on the hard problems that are not well solved either by rules, which is sort of the current state of the art, or machine learning. And people have tried machine learning, but it doesn't work that well. They're happy if they're in the 90s, 95%, 92%, but that's for the government or somebody else. You don't want to be 5% wrong or 8% wrong. That's really, really not acceptable. And to run the math that fast, we'll get a little bit into the IP later, but it's not just the model building, but it's the inference engine being able to take that Bayes net and reconstruct it into a form that can run really well on a CPU. And Mark's 12 years at Raytheon working on operating systems for helicopters and fighter jets, he really learned how to have code that has zero mistakes. We uploaded our model into space. We've run it thousands of times, tens of thousands of times, zero mistakes, zero errors, fully explainable. no dynamically allocated RAM, so very, very good memory footprint.
Hmm.
That takes a combination of the aerospace and running at the edge, plus the mathematics of Bayes nets and some real innovations that have taken it, say, 100 times, 1,000 times for what Bayes nets and logical AI was doing before.
Yeah, so I mean, it's a fascinating area. I mean, it's one that I think very few people have a handle on, and Mark and you are one of the very few. What I wanted to now maybe dive into is the section of why this matters for investors and the problem of how satellites actually die. And let's ground this in a real failure. You've told the story of a satellite that was lost to thermal runaway, not because nobody had thought about the risk, but because the handwritten rule, as you mentioned with Sherlock,
Yeah.
that was supposed to catch it, never fired. Thermal runaway didn't switch off the switch when it found that. And you have sensor readings that didn't quite match the pattern the engineers had imagined years earlier, because these satellites are up there for quite a few years. I can't imagine why that's still the state of the art, but that is the state of the art on spacecraft today. These if-then rules written on the ground years before the failure, so they couldn't predict what would happen. What does PiLogic's manifest engine do differently in that exact moment?
Well, one of the easiest ways will be when we show some of the screenshots or some of the application, what the data looks like. But first, quickly, the reason they use rules is because they run very fast and they're fully explainable to an engineer. And
True.
so that's very important. And so ours run just as fast, are just as explainable. But in addition to having a rule or a threshold, it can reason about other things. So, for an example, it will say, if my battery is depleting faster than normal, that might be a sign that I'm overheating. And therefore, even if there's no, if this heat sensor hasn't hit a threshold, switch to an alternative backup source and see if something happens with that. And things where um, a
And I
human,
think
a
it's that
smart
figure 3 brings that nicely in. We can
figure
zoom
three
that
brings
in,
that
yeah.
very nicely in. Yeah, for those who can see it, they can look at it. For those who not, they can download it. So rather than a human having to go to multiple different sources and try to figure out what's going on with every part of my system, the PiLogic model is able to reason about that in close to real time, so in 1 or 2 tenths of a millisecond. And
Mm.
so it will find, and we've done this for multiple customers, it will find when that dangerous temperature or when that single part is starting to degrade. It will reason from that, from things that are not directly measurable. And that's really the strength of Bayesian inference, is that it is very, very good under uncertainty and not great sensors at reasoning back to causes.
So how does
And
it know that the switch is stuck or open or has failed or maybe is failing? I mean, how does it do that? Yeah.
so it depends on what the failure is. It will see that other parts of the system are not behaving as they should, and it will reason then to the likelihood of that behavior not being regular. And it's especially strong if one or multiple sensors are not reading well,
Mm.
because it doesn't need those particular sensors to reason about what's going on with the system. It can use all of the hundreds of sensors in the system to figure out what's going on. Where the human is often fixated on, well, what's my temperature saying? Or what is this sensor saying? Rather than having, it's hard in your mind to have hundreds of components and hundreds of sensors all fully present and what their relationships to each other are. And one of the big insights we had was, and one of the reasons people haven't used causal models before, is that each configuration needs a model that understands that particular configuration. And so we've built automation tools where an engineer can say, this is my system, and our inference engine will automatically read that in and build a model that's specific to that configuration or that satellite. And I can
Very
show that
tailored and customized. Yeah.
perfectly tailored to that specific instance.
And done in weeks or days rather than months or years, yeah?
Yeah, so for Air Force Research Lab, it took them about a week to get all of the configuration and everything together in a JSON file, and then it took us 45 minutes to read that into our inference engine. So in less than a week, we had something that was running for them. We've now delivered milestone 2 in less than a month to Air Force Research Lab, and they were expecting a 2-year partnership, and we're delivering the outcomes of that in weeks.
Wow. That's congratulations on that. Putting the investor lens on, what did Scout and Seraphim see in PiLogic that was different to the rest? For investors in our audience, your seed round was led by Scout, Brad Harrison's national security specialist fund, and Seraphim Space with Sovereign Capital Flex out of Berlin and FN Fund and Gokul Rajaram, which I think is quite unusual, or maybe he's seeing something that the rest were seeing. And Seraphim's Andre Rosner, who I've spoken to, said the space industry is still rife with rules-based systems and humans in the loop.
Yep.
And you've mentioned this before, often for the lack of viable alternatives. And as I mentioned, the state of the art. What's the size of the inefficiency, and what's the market you're actually attacking?
Well, I mean, these models are much broader than just space. So you could apply that to cyber, you can apply that to oil and gas, to electrical systems, to advanced manufacturing. But just diagnostics and radar are both tens of billions of dollar market in aerospace and defense. What both Brad and Andre saw is they're very close to the customer, and the customer was not well served, is not well served by generative AI and agentic AI. They've tried it, it doesn't work, and they're sort of stuck. They want to use AI. They're being told you have to use AI, but that type of AI doesn't work well for them. And logical inference and probabilistic inference hasn't really it hasn't had a specialist like Mark who understood space, the edge, Google engineering, PhD, taking what Yuda Pearl and Anna Darwich did much further, combining all of that and building models specific to that problem domain. So you can't just go get a generic Bayes model and run it for space. That won't work. You need one that's customized for that problem set. So both Andre with space and Brad for the military community, they saw, oh my gosh, this is what that customer has been looking for. And that's why even with 5 people, we are going to do millions of revenue and are growing very, very fast because the demand for this is so strong. Even as a very young company, we've won multiple government contracts that often take years to win, and we've been able to win those very quickly. So the demand is very, very high for solving some of these hard problems.
Mm, mm, mm. And then maybe let's dive into your live demo. What are you seeing, and how's Sherlock detecting?
Happy to. So Astranis is one of our design partners that we work with. This is looking a little bit at the way a customer would work with us. You come in, you have a list of your models. You want to instantiate a new model. They use a system called MicroCap to do their EPS design, their electrical and power system design. So that's what they design their block diagrams, their wiring, everything that goes into that electrical system. So they're able to download a MicroCap file, in this case, Model 14, in a JSON format. They update that. They can look at sort of how many queries per second they want to do on that, what the model type is. And then it takes about 20 minutes. We check everything on it. Sometimes you have to iterate a little bit. It goes through and says, yes, this is a valid model. Electricity runs through this. The electrical engineer can go through and check voltage and power and do some sense checking to make sure that everything is right. And so this is sort of the first part, the model building. And when you can use that when you're designing a satellite, you can do that hardware on the ground, so flat sat, which is what we're doing with AFRL. Or once this model is instantiated, push it up and run it in a container on a satellite. And we have a customer that is running it in orbit. So that's kind of the pre-deployment. Then when you deploy it, you can read the outcome on the ground. What I'm going to show are a customer that are using our model in their operations room. So they're using it as a way for their operator to get root cause analysis of what's going on with their satellite. So in the first instance, right now we're looking at voltage telemetry. The voltage telemetry at the top, it's close to zero, then it jumps up to about 50 volts. You're looking at what's coming from the battery, what's coming from the solar array, and at the bottom, inference is matching what your telemetry is saying exactly. And in this case, a human operator knows what's going on. It's totally clear. They don't need advanced inference. But in the next examples, they really do. So now we have what the telemetry looks like on another one of the sensors, and you're trying to reason about the same situation, which is, do I have voltage flowing or not? And from the sensor, you have no idea. And this is where a threshold wouldn't work either. Neither a Boolean logic sensor, which is saying if it switches, then do something, you can't see any discernible switch there, or a threshold sensor that says if it goes above 40 volts or above 50 volts, then take this action. So these are basic examples, but imagine this across hundreds of sensors, hundreds of components. And for many of these, like thermal runaways, in 5 to 10 minutes, you can lose a satellite. Batteries, less than a day, you lose the satellite. Comms, if you lose communications and don't have a backup, then you never talk to your satellite again. So these are things that very, very quickly happen. So this is actual data. Many more examples of that. You have multiple sensors. You're trying to reason what's going on.
So Johannes, if I could just go back to the last slide, yeah,
Yep.
is the you see all the dots there? Is the bottom what your inference model is picking out of that?
Correct. The bottom is what the model posteriors are, so what the reasoning model is doing. And this can
Wow,
also,
and you wouldn't be able to do that as a human, yeah? It's like,
you would not be able to do that as a human. You would be able to do it as a human if you went to multiple other screens and sort of puzzled together. So an example would be going to the solar array and saying there's nothing coming from the solar array. Okay, therefore it can't be from the solar array. Or I have 50 volts flowing into another part of my system. Now I don't have 50 volts flowing into another part of my system. So as a human, you could, but you would have to know where to look, and you would have to go to multiple places, and
and
you
you might
might
be
not
too
have
late, yeah?
time. Yeah, you'd probably be too late. So just lots more examples like this, which is here you have multiple sensors. Often you have sensors that are disagreeing, and so either you as a
Explain
human,
how there's a disagreement in this slide.
well, it's about the same noise profile to start with, and then the second sensor jumps up to a specific reading
Mhm.
where the first sensor does not. And so here you
Oh,
have to decide which of those two sensors do you think is more accurate, and our model believes that that second sensor is more accurate.
okay, right.
So again, a human could do this across many, many sensors, but it takes a lot of work, and you don't always have the sensors side by side.
And you got time against you as well, yeah?
And you have time against you. So a couple different use cases. We see the Air Force and Air Force research labs wanting to do autonomy, but they have a concept of trusted autonomy, and they want to move from person in the loop or man in the loop, which means the person has to sort of check the box and okay an autonomous action, to somebody being notified, but the autonomous action happens. So you're still sort of in the flow of the information, but you're not a barrier to make it happen. And then they want to move towards non-24-hour operations so that it does it autonomously unless there's something that's an anomaly that's out of nominal. And then the human is alerted, but doesn't have to work all night. You don't have to man the systems 24/7. We have other customers who man their systems 24/7, and others who are trying to move more towards autonomy. And again, as as your number of satellites grow and as the complexity of that grows, human operators can't physically manage that. And just from a cost perspective, you can't have one operator per few satellites. If you have thousands of satellites, you can't have hundreds and hundreds of people sort of managing all of them all the time.
Yeah, and so that's the first product that you have. Now let's move to your second engine, Resolve, your radar tracking product. And here's the topical hook. Since February, the war with Iran has produced the largest documented GPS jamming event in maritime history. You got all those ships moving around, and a lot of them don't want to be seen or are being jammed. So you have thousands of vessels reporting interference in the Gulf within the first 24 hours of that war. And in Ukraine, you have quasi the same sort of situation, but on a larger scale, maybe,
Right.
where you have electromagnetic spectrum is now the most contested terrain. Yeah, and Russia being well ahead in that field. In that world, sensors like constantly. You have always or a lot of false detections,
Yeah.
misdetections, positions that are simply wrong or being spoofed.
Yeah.
Um, what does Resolve do with that noise that a classical Kalman filter, the 60-year-old standard cannot?
So the Kalman filter is the ideal algorithm when things are going well. And so if you're at an airport, if it's not jammed, it performs very, very well. But in our research, working with Riverside Research, which is one of the leading labs looking at radar, they've been working on it for, I think, 70 years. Looking at it in contested environments, as you said, the data is much more sparse. And so we have kind of a dual approach to that. We use an exact search algorithm to identify if there's a track there, whether it's the same track as in a prior time slice. And Mark, of course, coming from Google, is a search specialist. Search is not just finding things on the internet. Search is a whole field of identifying things. So we use an exact search algorithm for that. And then we use Bayesian inference with better physics models than the Kalman filter. So the Kalman filter is, in fact, a very simple Bayes net that's
Mhm.
optimized to run in real time. So our approach was, rather than running in real time, have a slight delay, milliseconds of delay. It's not a long delay, but have a slight delay and have a more sophisticated two-part algorithm. And if you quantify that, so you have mean squared error on the vertical axis and you have false negative noise on the horizontal axis. If you go out into 85% false negative noise, this means that 80 to 85% of the data is either spoofed or hidden or wrong. We are able to perform the same or better than the Kalman filter is with 0% noise. So
Give me
our
an example of that. What application is it? Drones flying close together, or crossing paths, or
That
planes, or
that's so that's one of drones is one of the biggest areas, particularly the larger, more dangerous drones. And then this data is synthetic rocket data, where a rocket, a ballistic missile, is coming out of the atmosphere and then back into the atmosphere. So the
Mhm.
two main areas of our research are on drones and on rockets. So think Golden Dome, think space-based interceptors, running these algorithms in space, being able to make judgments very, very quickly in space and more accurately is incredibly important for rocket tracking. And then, yeah, for the ground, it's mainly drones, although we're also in talks with some of the major EVTOL providers. Non-traditional flight is much more difficult for common algorithms.
Mhm.
So being able to track something that can vertically take off and fly at angles, sort of the number of possible places that that can be is much, much greater than something that has a consistent flight. So imagine an airplane, it can't stop, it can't vertically go up and down. It's going 300 miles an hour. It's going to vary a little bit, but basically it's going around 300 miles an hour. While an eVTOL or drones, the problem space is much bigger because the maneuverability and what they can do is so much broader. And so
Mhm.
it's very computationally heavy to try to figure out all of those options. And so having probability, being able to use probability, so Bayesian inference plus exact search, narrows the field of what it can do physically and makes you able to much better compute where it can go.
And I think we had also here figure 4, which gives us sort of on the Kalman filter on the one side and the exact inference, and it sort of shows exactly the same as what you've just shown in your models. Is there anything that you want to explain more in detail about what is happening here from between the Kalman filter and the exact filter? Because it looks as if the exact filter is smoothing out all the noise, and the Kalman is very clunky.
It's very choppy. And so from an operator's perspective, if you're trying to predict where something is or is going, it's under a contested environment, it's almost impossible to do in this Kalman filter scenario, because the noise is pushing the Kalman filter away from where the truth is, both above and below. And we're talking about football fields of distance, right? It's getting it wrong by 100 yards, 100 meters, 1,000 meters. It's getting it very, very wrong. And so both if you're the one trying to track it and make decisions with it, you really want much, much more accuracy than that.
Yeah, so it's basically accuracy in the physical world in AI. Maybe bringing that into perspective with an example, and this might be one of the most loaded capabilities that you have with your radar. When a satellite suddenly fails today, a government, and also with your other product, government faces a terrifying question. I mean, was that the sun? Was it a solar flare? Or was that an attack? And the wrong answer in either direction is an escalation or blindness. I mean, either are worse, or not good
Yeah,
solutions.
they're
Yeah,
both very bad. Yeah.
yeah. And as you've described it publicly, your system works by exact elimination. If it's not internal, not manufacturing defect, not a solar event, what remains is, of course, electronic warfare or cyber. Could you walk us through how a machine reasons its way to, we believe this was an attack, as an exact sort of reply, rather than maybe this was not certain, or where the
It
machine's
it's
certainty
still
has to
it's
stop, where
still
you're not so sure about that.
yeah,
But
yeah, it's still probabilistic. So you're excluding them and saying the other ones have very low probability or almost no probability. The way you model that is you have a bunch of potential causes of things going wrong in your system.
mm,
And so one of those is external factors, whether that's kinetic, so something in fact hitting it, or cyber or electronic warfare. And so as the system is going through, is it the sensor itself that's broken? So there's no other thing. Nope, the sensor's right. What are the other potential causes? It can very quickly reduce that down and say, I think it's highly likely that it be cyber or electronic warfare. If it's kinetic, it could be natural. So it could be space debris. It could be something else. In order to narrow it even further, there are other sources of data like space weather data. Starlink themselves have a bunch of data that the government is buying, that Starlink is looking around what else is out there. So what else is in proximity? Are there any adversaries that are in proximity, either above my orbit, below my orbit, close in the orbit? So matching those together, one can get a quite accurate picture. Getting more detailed starts to get more into the classified of what the data is precisely, but generally that's what the approach is.
yeah, and we're seeing this also with the high demand on one of our portfolio companies called Lookup Space, which basically identifies objects in space. So you're giving it more certainty about what's happening, but live in milliseconds in space, right?
Right, right. And you don't want to get that wrong. So
No.
even if you think it's most likely something that's outside your system, you think most likely it's an adversary, you normally want to have that confirmed by something else before you make an arbitrary decision on it.
Well, exactly. Yeah. Now, moving maybe on and zooming out to the two defining defense programs of this decade, we have Ukraine, the side that turns sensor noise into decisions faster, wins over there. We heard exactly that from Tekeva's Ricardo Mendez on our show, a couple of shows before this, where he has 50,000 combat flight hours behind him. And in Washington, as you mentioned, the Golden Dome is being architected around tracking enormous numbers of objects with no tolerance for error. And that is exactly the point.
Yep.
And it's under jamming conditions in real time. Yeah. Where does exact AI slot into that stack? And what does an army that has it do to an army that doesn't have it?
Well, it stacks up in two places. The first is if you're fielding thousands of satellites, you need to know how are they performing? Can I self-heal them? Are they going to do what they're supposed to be doing? Is there something going wrong with them? So our ability to help them understand the health state, both of older satellites and of their newer satellites. And even if it's passing between ground stations, our models are small enough that we can send sort of health state between satellites. So at the moment, satellites will go dark for half an hour or so between ground stations, and you don't know, is somebody doing something to my satellite? Is it going to be fine? Or is it going to be in a safe mode because there was a software update or a software glitch? Never send a tank into battle without knowing, is it ready to go? Is its payload ready to go? Is everything ready to go? So the first thing is you want to know what's the status and keep it healthy of all of your satellites. And so that's where our diagnostics, sort of the self-healing, starting to automate that more and more as the government builds more trust in autonomy, that it's provable, it's verifiable based on first engineering principles. So I mean, it just means you field much better assets that stay up better and that you have better visibility on. And then the second one is exactly what you were saying, which is it's a multi-tiered, so from very, very high Earth orbit, lunar, cislunar, high Earth orbit, low Earth orbit, from the ground. And so you're doing sensor fusion across many, many different domains, not just radar. We're starting to look at infrared, optical, sort of other phenomenologies that you're trying to fuse together. This is what my radar sees. This is what my infrared sees. What should I believe? And so we're starting to layer on top of just replacing the common filter with our tracking algorithm is then saying, okay, now we need to add other sensor types and sensor fusion above that and causal reasoning above that. So we have a long roadmap inside that space domain awareness and space perception. But yeah, it's one of the three or four most important things in Golden Dome and space-based interceptors, which is if you can't see it and track it, then it doesn't matter that you've gotten everything up there. It doesn't matter that you have something that's fast enough to go get it. If you can't see it and track it, it doesn't work.
It's invisible, yeah. To you, it might as well not be there, yeah. Coming back to your Air Force Research Labs agreement, it came with something telling, sponsorship for top secret clearance and support from Space Systems Command. Governments don't do that casually without crossing any lines. What's the problem that they are hoping you'll solve for aging fleets and contested orbits?
The two that we've just been talking about. So diagnostics and better tracking and sensor fusion, they are close to the top of their list. And a lot of top secret platforms, which have those needs. We've built all of our systems as non-ITAR, as commercial software, so we can sell to partners in Europe and Australia, friends of the US. But now we're getting strong demand signal to take those systems high side and start delivering them to platforms that otherwise we wouldn't be able to deliver software to.
And that brings me to my next point about, since February, every government in the Middle East has watched its navigation, its ships, and its airspace get scrambled. Has this year changed the conversation you're having with these new
It
regions?
well,
Urgency?
we're not having conversations with those regions, but the US, of course, is operating in those regions, and so the urgency, of course, is much greater.
Mm-hmm.
Yeah.
Well, that's very telling. And maybe moving on to the next point about how governments buy now. I was at a meeting with FUZE, the guys from the US Army came over here
Yep.
to London. Here's a structural question for policymakers listening. Your US Air Force Research Labs deal is a crater. No
Yep.
money changes hands, but you get their test bed, their
Yep.
engineers, demo to military customers, which is invaluable,
Yep.
and a clearance path. Meanwhile, the US Army has just stood up FUZE, which I just mentioned, which we had the guys here in London. It's an engine for innovation that explicitly says it invests like a venture capitalist, roughly $750 million a year, non-dilutive capital, so it's grants or payments. What does that mean for a 5-person startup like yourselves on the receiving end? Is defense procurement genuinely changing, or is it just theater? And what should Europe copy?
So I would say it's not just theater. I would say there's some things that will always be difficult. So getting into the big long-term contracts is always very hard. They do have SIBR programs, STTR programs, FUZE. We will be announcing winning some of those soon, and those go up to $3 million. Those are great. So those will probably be our first $1 million contracts, and so that's great for a 5-person company. The other thing is that we've always believed that some of the cutting commercial edge companies are also really, really important to work with. It both validates what we do with the government, but also they're much faster partners. So, for instance, Astranis as a design partner, they move much, much faster than a government customer. And so the number of innovation cycles we can do with private customers, whether they're data centers in space, whether they're in high Earth orbit like Astranis, means that we innovate what we're delivering. And then when we go back to a government customer, we're much further ahead than if we sort of went through their buying cycles and their slower innovation cycles.
Mm-hmm. And I mean, you mentioned it right at the beginning about the orbital edge and data centers in space. You have compute efficiency sessions suddenly look prophetic. I mean, because of what you're doing, you need less compute, you need less of everything. In November, I think NVIDIA backed StarCloud put the first H100 GPU into orbit.
Yeah.
By December, it trained the first language model in space. By March, it was a billion-dollar company, with Musk talking about terawatt of orbital compute and Bezos predicting gigawatt data centers in space. Every one of those satellites is an asset that absolutely cannot be allowed to die. And of course, you can't phone home for help. um,
Right. And you want to run it on a CPU because it's often the GPUs that melt or that get too hot. So you
yeah.
want you want to run it. So those are our ideal customers. We've been talking to Phil for a long time, who's the founder of StarCloud. We like them very much. And of course, talking to their competitors, there are lots of other people that are putting, whether it's data centers or whether it's inference infrastructure to do more inference in space. So we see that as a massive market for us. And if we can deliver something that works right away and that they don't have to send up at launch, it makes a huge difference because we're not on their critical path to launch and test. We can test it on flat sets on the ground, and then we can set it up and test it for a little bit. If we want to change it, we send another
Mm.
code base up. It's very, very light. So we see that as a huge, huge growing customer base for us. And we believe the government will have to buy a lot of that because in order to do Golden Dome and in order to have sensor fusion in space, you don't need a full data center, but you need to run a lot of compute and a lot of math in space that we currently are not able to do. And so having both light models that can do that and a government customer that's pushing more and more inference up to space, um, along with the SpaceX's IPO,
Mm.
and some of those businesses taking off, has really put wind in our sails.
Yeah, and then maybe then moving straight into the other part, which is about competition and moats and looking ahead. It's quite unusual in this case because the actual angel investor who have based this moat test on is one of your investors.
Yeah,
Um,
that's great. In fact, I'm going to send this to Gokul afterwards and see what he thinks about the which moats we have.
yeah, so can you maybe walk me through figure 5, if you can bring that in, where we look at all the different points? He talks about
Do you
these
want
8
figure
moats. Yeah.
6 or do you want figure 5 where we've given
Yeah,
what
or
we?
maybe let's start with figure 6 and then move into figure 5, yeah?
Yeah. So if we look at figure 6, the ones that I would focus on for us are the data and the IP. So the ability to automate the model building, to be able to run on the edge, to have broken some of the barriers in terms of how complex problems we can solve,
Mm,
which are years of research by the UCLA lab, and they have an academic version, which they win academic competitions with. But it took somebody like Mark with his engineering from Raytheon and then Google to commercialize it. So really the data and IP is the strongest, kind of the strongest moat and the most difficult. And for that, it's a dual path, trade secret on the main secret sauce, and then patents on some of the software process and sort of model building process around it. So protect parts of it through patent, but a majority of it through trade secret. Sort of regulatory and getting into the government and getting them to trust and sign off on it takes a long time, and is difficult, and you need clearance for some of it. And so we have jumped through a lot of those hoops and are jumping through some of those hoops. If we look at figure 5, as you can see, if you're just listening to it, the figures are also downloadable in the description. And that leads to number 5, which is distribution. If you don't have that regulatory piece, so clean cap table, all U.S. Citizens, all 5 of us are U.S. citizens, allow us to work in those environments. So we can sell into the government. We have contracts with SpaceWorks, Air Force Research Labs, Space Systems Command, SSC. So those are really the 3 moats that we have. We will go into the workflow one, because once Astranis or our customers begin to use our model to validate all of the designs that they build, and once it's the root cause analyzer of all of the data that they have and the way they run autonomy on satellite, then to tear it out is really, really hard, and you can't like for like replace it with anything else. The rules tend to cover 40 to 50% of the edge cases. We cover closer to 90%, 95%. So we have almost 100% more coverage than if they replace what we were doing with rules. So workflow is the next one that we're sort of trying to crack, is get into the workflow of our customers, make it easy to integrate with the tools that they have, so that it's a no-brainer to use us for design, test, and operations, kind of the 3 large parts of what they're doing. And then once we have the workflow, then it becomes about scale. So if we can work with the Lockheeds, with the Airbuses, with the Boeings, then suddenly we have very, very large scale, and we become hard to replace because we become more the default. So our goal for Space Systems Command is that they mandate our capability across all of their partners. And since no one else is delivering that capability and that workflow, we begin to scale as sort of the system of record to do autonomy and diagnostics. And then the physical infrastructure, our strength there is that we don't need it, that we don't need the billions of dollars of data and of training and of compute. So we figured out a way to do it really, really light. And so it's very hard for a competitor to be able to do it that light, to build models in the kilobytes and low megabytes and deliver those at the edge. And then it's not a two-sided market, but there are network effects in that as we talk to the primes are serving the government. If the government wants our capability, makes it more likely for the prime to use it. We're working with some of the primes. They love what we're doing. They're selling it to the government, makes it more likely for the government to buy it. So it's network more similar to number 5, distribution. So that's kind of the way I would look at it, is that data IP is our strongest, regulatory and distribution are 2 that we're working on. Workflow would be the next one, and then after that, it's scaling.
And then with that, you've hit the 4 minimum that Google has asked you to
Right,
hit, right? So,
which you don't have to have at the day of starting the company, but that
oh,
you
is that you
that
that
you
you
need to
can
grow
progress
it.
to sustainability in
Yes.
on those and maybe moving to the next point around beyond space, and you've already mentioned about EVTOLs and air taxis heading for certification, electric fleets grids and under-strain compressors in energy industry. How far does this architecture travel beyond aerospace? You sort of touched on it at the start. Just wanted to get
Yeah.
more insight into that and how you see that.
So the way to think about it is it takes us between 3 months and 6 months to build a model template for a new industry or for a new type of problem. And that variance between 3 months and 6 months is how well do we know it? How complex is it? What we love is where part of the problem is very well known. So the physics or certain attributes are very well known, but what's not known is the state or predicting what's going on at the moment. And so, for instance, if we did something for EVTOLs who we're in talks with, one of the questions we've been working on is how bearings wear and parts of the movable EVTOL wear. They wear out much faster than a fixed wing airplane because they have to move and they degrade faster. And so you can't really just do it with flight hours. Typically, you would say after this many flight hours, then I need to replace the bearings or I need to replace certain parts. But there are other things like, is there sand? Is there water? How is the acceleration? How often does it change from vertical to horizontal? What are the types of flight that it's doing? Are there high winds or extra stresses on it that a typical flight doesn't have? And all of those affect how bearings wear. And so an example of models that we've looked at is how do you reason about that given you don't have a direct sensor on how those bearings have worn and you can't put a sensor in there? How do you use the other evidence about how it's been flown, what else is happening, the sound, the effectiveness or the efficiency of some of the things, and use all of those to reason what's the health state of my bearings? Do I need to replace those out of my normal pattern or not? Or conversely, are they going to last a lot longer and I shouldn't spend $100,000 replacing them because they're totally fine? So that's an example. For compressors, we've talked to some of the big oil and gas companies. Again, there isn't a direct sensor to be able to reason about some of those. And so, again, similar, we would spend some months studying the problem, working with a combination of the theoretical maths of it, and then the people in the field who watch them explode or watch them break down, some of the practical nitty-gritty of what happens. And our models combine both of those to be able to reason well about what's going on.
I mean, that's fantastic. I mean, just want to maybe tie it off and close it off in something we always ask for our audience, so investors, sovereign wealth funds, and policymakers who want to understand where exactly or how exactly they can read about exact AI, machine reasoning, and the future of autonomous systems, and where they're heading. Which books would you recommend our listeners, and what is a single thing you want them to take away from this conversation?
Well, the one that's English readable is called The Book of Why by Yuda Pearl, spelled Udea Pearl, but pronounced Yuda Pearl. That's probably the best book on causality and on Bayes nets. That's what I would start with. And I think the main takeaway is that generative AI is not the only type of AI. There's exact search, there's reasoning, there's Bayesian inference, there's logical inference. And so when they think about AI, think about what is the problem that I'm trying to solve? Is that best solved by statistical methods or mathematical methods, or by an unsupervised learning method, or by a supervised learning method? So that AI is much more multifaceted than most people think. And
Mm.
there are many types of AI that are super good at a certain type of problem, like exact search is the best in the world at a certain type of problem and not good at other types of problems. So think about matching the problem set to the right type of AI.
Mm. And you mentioned another book, I think it was Darwich's Modeling and Reasoning with Bayesian Networks.
So for those who want to go more into the math, Adnan Darwich now runs the automated reasoning group at UCLA, and that's more textbooky and more
Or
going into
academic, yeah,
more
basically, yeah.
academic. Yeah, and Adnan Darwich has great YouTube videos. So looking up Bayesian inference and Adnan Darwich. You find lots of YouTube videos of him teaching classes and talking about it, and that's an approachable way, if you don't want to read the full book, is you can dip into some of his explanations and classes on YouTube.
Well, fantastic, and thanks so much for coming on board. And really, really love to see you again after so many years. And would love when you're passing through London, do come by. And look forward to meeting up with you. And good luck with your PiLogic. Yeah, it's a
Thank you
fantastic
very much.
product.
Yeah, wonderful being on here, and thank you for being such a well-prepared host.
Thank you for listening. I really appreciate it. And I will see you in our next episode soon. Don't forget to like, subscribe, and leave a review so we can keep growing and reaching more people. If you're an LP interested in learning about space tech, defense tech, and security, including cybersecurity investment opportunities, let's chat.